Alright, welcome back to our function slides. Let's go through and finish them finally. So we learned about a bunch of cool stuff last time. The stack was a place, right? It is a place in memory where functions store their local variables, and also like who to return back to is always the person underneath them on the stack. We learned about references and passing references to functions. That lets us like mess with somebody else's memory, give variables a second name, a third name. References are really good for like when you want to pass something that's large as well. It saves memory because you're not copying it anymore. Because usually when you have a normal parameter, call by value parameter, it's being copied. We don't like that. This is a good example though. We also learned about multiple files, right? Multiple files that we can like put all our stuff in, make our own libraries. I want to come back to this idea though. Like sometimes, like I think the example that I gave here was like summing up the values of a vector. When you pass that by reference, you don't get a copy, you get that other person's vector, and you can actually mess with it, can't you? That's not good. Like you should have just summed it only. You shouldn't be allowed to mess with the indices. So there's an answer to that. So const parameters are the secret here. So I'll try to answer this question, right? So here's the setup. It's that same idea. Like I would like the memory savings that comes with using references in function parameters. Like when somebody like I want to be able to sum, right, a vector. So int, call it sum, like I'll put some space here for a reason, vector int v. So if you do it like this, right, it's going to copy the vector. We don't like that. To save on copying, you put the reference here. But you're able to mess with that person's vector, right? You're able to go to like v at 0 and mess with it and set it to like, I don't know, something else. Set it to 42. You're able to touch somebody else's memory when you do it like this, right? That's what references give you. That's one of the powers. Just like in our inc function that I showed you, void inc took an int by reference, and we wanted that to be able to change somebody else's memory in that case. So like that's messing with like main's int variable. We're calling it I for a split second. That's the beauty of references. But sometimes in like a sum function, you want to just take the vector and not copy it. You just want to not copy the thing to save space and time. But you don't want to be allowed to do something like this. Like that's not good. We don't like that ability. All right. The secret is what you can do is you can put the word const out in front of the type name. You put it right there. Okay, const. And that essentially makes the parameter that was passed to you a constant. All right, because we know what const is already. It's something that you can't change. It makes what was ever passed to you, it gets like the space savings. It doesn't copy it. It creates a reference. But you cannot mess with it. You can go to indices, but you cannot change the indices. So that's pretty neat. All right. Why does this work? First of all, and then I'll go to the example in code. Why does this work? Why are you allowed to like pass something that was not constant? Right? Because the goal is like you're passing something into here in main. Like you're trying to call sum with your own normal vector that is of course not const. You're trying to pass your own constant vector or your own normal non-constant vector into here. Why is that allowed? All right, because that is allowed. And I'll show that in code if that's not making sense yet. So the reason this is going to work is go back to the dreamland. You can assign non-constant variables into constant variables. All right, so like say you did this. Int x equals 42. You can put in a constant int, right? Const int y. You can make that x. So you're essentially putting a non-constant thing into a constant thing. Does that make sense? Like you're allowed to do that, and so that means you're allowed to pass non-constant vectors to one that expected a const reference to a vector. Okay, those are a lot of words, and I will show that in code in a second. Okay, just like the second you do that, though, that means like you can pass your normal non-const variable to something that took a const parameter. So let's start with the sum of a vector function. You'll try. I think it'll make more sense. You'll see what I mean. Okay, so let's make that. So const, not CPP. Oops. 2 P's. There we go. So yeah, if I want vectors, I'll include the vector library. But yeah, I think those words are just hard to understand. Like that's a lot of weird stuff that I just said. So let's talk about it in general. So what I meant is you can start with a normal int and shove that into a constant int. That is totally fine. Everybody's happy. All right, that is okay. It's being copied. I hope that makes sense. And so you can do x++, it's still fine to mess with your original x, but the one that you put into the constant, now that's totally not valid. You try to do y++, so it won't even compile. Okay, That's kind of the point of putting something into a constant. You put it there and it never changes once it's there, okay? But you can put a non-constant thing into a const. That's what I'm trying to say, okay? And that's why constant reference parameters are going to be cool, okay? So let's make a vector. 1, 2, 3, 4, 5. Oh gosh, what just happened? That's really weird. I pressed a weird key. So there's my vector. And let's make a sum vector function that we can call. Like I want to call it like this. I want to say sum vector. It'll take my vector v and sum up all the values and give back the sum. So that's going to be int sum vector. And it'll take a vector int v. Right now this is by copying it, right? This is by value. So it's going to copy it. We don't like that. And so to get the space savings, you can change that to a reference parameter. That's totally allowed, right? And that's okay. And then let's go through and sum everything. Let's be like int sum equals 0 for every element in the vector v, added into the sum, and then return that final sum that we've computed. Right, so that's the normal sum vector function. It'll work. We took it by reference, so we got some nice space savings. We didn't copy the vector as it was passed, and that's really good. And I get my 15, that's the answer. But look at what I can do right now to this vector v, and it's going to mess with main's vector v. I can say v at 0 equals 42. That is disgusting, right? This should not be allowed to do that. Does that make sense? But it is, and it's messing with main's v because I'm passing it as a reference. So not only is the sum going to be the wrong answer now, it's just whenever main looks at the vector v, the index 0 has now been changed to 42 for sure. All right, I've just messed with its own memory because I took it by reference. All right, we'd like this to not be allowed. To be impossible is a quicker way to say that. All right, so the secret is you put const right here. You say const vector int reference v, which is definitely a mouthful, and now suddenly this becomes invalid. Now it won't even compile, and that's perfect. Assignment of read-only location, and so it makes the vector that it's looking at read-only for the duration of this function. Isn't that nice? So now it won't even compile. It will work now though. If I get rid of that offending line, it will do the right thing. And this is enforcing the fact that the vector that I pass, even though I'm taking it as a reference, I'm not allowed to touch it for the duration of this function call. All right. And notice that the vector was not const. I'm passing a non-const thing up into here. That is totally fine. Because remember in the dreamland, what's going on is that somebody's saying const vector int reference v equals mains v. All right. It's just kind of like this line. All right, I hope that makes a little bit of sense at least. That's what's going on, and that's why it's allowed. It's just for the duration of this function call, it's treating it like a constant. It isn't like the deep down in memory. It's not really something that is a constant. This is just a normal vector, but we're allowed to pass it, and it will be converted into a const for the duration of the call. All right, and that allows us to like never mess up. So use const parameters as much as you possibly can. All right, space savings, and then you make sure that you're not touching somebody's memory. Okay. So yeah, once you do that, your function cannot change the value that was passed to you, even if it was non-const, and that's perfect with references. All right, so use const references as much as you can, and you'll get space savings, plus you'll be confident that you can't make any silly mistakes because the compiler will catch it for you. All right, so that's a cool little topic. I wanted to do that first, and now I want to switch gears to a CSCI 41 topic. All right. This is something called algorithm complexity. We want to like discover how to analyze the things that we write, the code that we write, the algorithms that we create. How complex are they? How fast will they be in terms of something? All right. This is a CSCI 41 topic. I'm not going to test you on it. Just me talking about it now will help you in future classes, and then also just make you a better programmer right now anyway. So like that's why I'm going here. I will not test you on any of this little subsection. Okay, that is my promise to you. But I promise that this is very, very good information. So it's worth paying attention and still watching. Okay? CSCI 41 will be much easier if you know this first. So yeah, essentially what we want to do is like ask this kind of question, like how fast is my program? Like how could I do better? If I have different options of this algorithm that I'm working on, like which one's the fastest? We can count seconds if we want to. There's a CTime library, and there's like a way to like look at the clock inside the computer and like just look at it twice in between your algorithm call, you'll know how long it took. Like, you can get numbers back, like, okay, my algorithm took 5 minutes to run on my computer. But that's not really a good number, because like my computer, as a teacher, I can't afford a very expensive computer, but some people, like with their fancy processors that are super fast, will take my program and maybe their processor's twice as fast as mine, then it'll run like in half the time. Does that make sense? So every processor's different. Like maybe my computer, its processor is 1.5 gigahertz. Have you heard this before? This symbol, this idea. What this means is, when you see this on like a processor, it means that your processor can run 1.5 billion operations per second. All right, and there are like 3 gigahertz processors as well. So that's the thing. And so the same program running on one of these is twice as fast, if that makes sense. So that's not really good. Like maybe you want to run your program on your microwaves processor or something, and then it's super slow. So we need a different way of determining like how fast the program is, because like if we run the same program on multiple processors and we get different answers, like we don't know what the real answer should be. So let's have a better way. Here's the better way. Instead of using processor speeds, we're just going to like count how many steps inside of the processor it took to do the answer. It took to get the answer. Okay? So yeah, because like there's always, like even on your microwave, a better program's a better program. It'll run faster than the naive way of doing things. All right? So what we're going to do is we're going to count what I like to call basic operations inside of our algorithms. All right? And each basic operation will pretend it's going to take 1 step of execution time inside of our processor. All right? That's what we're going to imagine right now. Once you get to CSCI 45, I will tell you a little bit more about like what really takes 1 step, but I want you to consider all of these things right now to take 1 step of execution time inside the processor. It won't really matter if I'm lying to you right now, and I am kind of lying. All right, so it's still okay. All right, just pretend right now. It's still going to work, what I'm trying to say. So pretend that all these things take 1 step of execution time inside of your processor, and some of these are true. All right. Some of these are true. Others, maybe they take 2 steps, really. It's not a big deal. So pretend they take 1 for this class. It's like any arithmetic, plus, minus, times, divide, modulus, any comparisons inside of an if statement. Pretend that all of those things take 1 step of execution time to get an answer inside of your processor. And we're just going to count those steps. All right? Same with like assignments into a variable. After it's done its work to assign a value into a variable, 1 step at a time. Printing something to see out. Assume that takes 1 step of execution time. This is the one where I'm really lying, but it's still a constant number, so it's not a big deal. So here's an example. Let's practice together this idea. So int x equals y times z plus 2, let's say. So that's supposed to be a z. That's a 2. Let me make the z a bit more pointy. There. All right, and then let's say I want to see out x after that. So let's count the basic operations in these 2 lines of code. That's my mini algorithm, okay? That's what I want to do, and I'm going to count those. So, okay, for the first line, what's happening? Well, it's going to compute this answer first, which is going to involve multiplying y times z. That's going to take 1 step of time to do that 1 multiplication, and then it gets the answer. And then it takes that answer and it adds it to 2, right? So that's another step of execution time. Take those 2 things, add them together, get a final answer. And then finally, it needs to shove that answer into a variable x. And so that is one last thing. That's the assignment part. All right, you take the final answer, put it into the variable, go into memory, write the thing. And so that's going to take 3 steps of execution time inside of our processor to run that 1 line. All right, and then finally, the next line to print to see out the 1 thing. There you go. It's 1 step of execution time. So in total, this little mini algorithm takes 4 steps of execution time inside of any processor. And that's nice, right? Then it doesn't matter if you're going to run it on your microwave or your super fast supercomputer. It's still going to take the same number of steps. And so if we just count steps, we can figure out if there were a better algorithm, all right? Because it'll take fewer steps in any processor. That's the goal. All right, there are plenty of things that are not basic operations. Anything other than these are non-basic operations. Like imagine you're summing through a vector. That is not a basic operation because it depends on the size of that vector, right? If it's a size 100 vector, it takes some time. If it's a size 1 million vector, you got to go through 1 million elements now. It's a completely different amount of work to be done, all right? Same with like calling a function. You have to count what's going on inside the body, count all the basic operations in that function's body. Okay, then you'll know how fast the function took. It's not a constant number a lot of the time. Maybe because maybe that function was some in the vector. You never know. Same with something like reading a bunch of values until the user types -1. You have no clue how many numbers the user is going to give you, so you can't like put a limit on any of that. Okay, could have been forever. But in general, a lot of things just that are single lines that don't do anything super fancy like call functions, you can imagine them to be basic or take a constant number of basic steps. All right, I hope that makes a little bit of sense. So with that in mind, try this. I'm going to go back to the slide once I explain this so you can pause it there and look and remember. But here's a loop. How many basic operations is this loop? All right. You don't know how big n is. You know what I is going to range between, but you have no clue what n is. So your answer needs to involve n, is my hint. All right, but try it. How many basic operations does this loop take where this is my definition of basic operations? All right, or here, let me even just like screenshot it and put it there for you. There, now you can just like pause the video, count those basic operations, and then come back and I'll show you how I think about it. All right. So we have to remember how for loops execute, right? So this for loop, what's it going to do first? It's going to run this line just once, right? This initialization line is going to be run once, and how many basic operations is that first line going to take? Well, let's just shove a value into a variable, so it's going to be 1. One basic operation to do just that, and then the rest of these are looped, aren't they? The rest of these are looped a certain number of times. So let's think about this. So let's count the basic operations of each piece. So we got this comparison, that's one basic operation. The C out is, you're printing 2 things. So the C out of that is 1, C out of end is the other one. So 2 for that one. And then the I++ is secretly, remember, doing 2 things. It's secretly shorthand for I equals I plus 1. So it has to do the addition, that's 1, and then the assignment of the answer, so that's 2. Okay, so that's the count of all of those. I hope that makes sense. Another question is, how many times are these being repeated? So it's in terms of n, right? So 1, you're going from 1 all the way to n inclusive, so you're looping n times. And so really, you're doing the body and the increment for sure n times. Does that make sense? You're doing that n times. And so, and then also the comparison. So it's condition, body, increment, it's n times, because you're looping through n different values. So the first one was just, like from this, it's contributing 1. And then from all these looped n times, it's what? 1, 2, 3, 4, 5 n times, though. Plus 5n. And then also, if you think about it carefully, the loop needs to finish. It needs to notice when it's done. And so after condition body increment one last time, after the nth time, it does need to check the condition one more time to notice that I is now bigger than n. Does that make sense? It needs to stop the loop. And so it's going to be one more basic operation. It's got to hit the condition one last time to stop the loop. And that is going to be the answer. All right? Did you get that? Do yell at me if you have any questions. But that's how I would count it. And so you can simplify that to 5n plus 2. And as n is large, I think you can imagine, like if n was 1,000,000, the plus 2 doesn't really matter. So this is, for all intents and purposes, the same as 5n, which looks like a line. All right? That's kind of the goal. And even the 5, as n is large, doesn't really matter too much. So like we really just say like this is a constant times n, and this is kind of the graph. As n gets larger, whatever the variable n was, we have a linear amount of more work to do. It's a line. Does that make sense? So like that's how many basic operations, and it's going to depend on this value of this variable. Isn't that cool? So like that's how fast it's going to run. That's how many steps it's going to take inside of your microwaves processor versus your laptop's processor. It doesn't matter. It's always going to be the same like that. So if you have a better algorithm that like always takes the same amount of time, you know that's always going to be faster regardless of your processor. That's where we're going with this. That's why we study this in CSCI 41. Okay? So just in general, to analyze an algorithm, you count all the basic operations that make it up, and then you try to find a formula for like how many steps the program takes in terms of something, usually in terms of whatever the user is going to give you. It's like usually like a size, something like that, like how many numbers are they giving you, stuff like that. And usually we use the capital N to mean that. Like whatever the user gave me, we'll call that N. All right, so I'm getting you practice with that because I used N here too. So yeah, in general, that's how you do it. And so let's think back to some stuff that we've done already. So like let's count the number of basic operations to do all these other things. So let's think about the difference between them. Some Like this is going to prove beyond a shadow of a doubt that some operations, some algorithms take longer than others. So for example, like to add two numbers inside of a processor, that's just one basic operation. No matter what the numbers were, even if it was like two giant numbers, they were both just ins. And so it took one step to do those things. And so that's called constant time, where it doesn't really matter. It's always going to take one step, or a constant number of steps of time inside the processor. To sum up n numbers, I think you can imagine that you need to start a sum variable and keep on adding each number one by one. So it's going to be some constant times that n that your numbers were, that many numbers. Because if you had more numbers, right, you had more numbers, it would take more work than fewer numbers to add them up. But it'll look like a line. So we call that linear time algorithm. Okay, that's what it looks like as the graph. And those are all easy compared to this, right? To draw an n by n box of stars, if you think about that carefully, well, just to print a single star, it takes one step of time. You're printing n squared stars, aren't you? And so there's going to be some constant times n squared if you do the analysis, maybe plus some extra stuff. But like that's going to be the biggest term. And so you see that that's going to kind of blow up a lot better, or a lot worse than the other ones. So like it's a lot more work because you got a lot more stars. It's a quadratic amount, right? Compared to a smaller number of stars. I hope that makes sense. So like this will take more time than these other algorithms. I hope you see that. So we call that polynomial time because it looks like a polynomial, n squared, n cubed, stuff like that. So if you think about this as you are writing your programs, it will make you a better programmer. And then also, if you don't care about that, it'll make you much better prepared for CSCI 41 if you have to take that class. Because this is like one of the things that we hit hard in CSCI 41. Okay, so you'll get a better grade if you pay attention to this. So I think that's what I wanted to say. So I will not test you on any of that I just said, but it's still a very, very good thing to know. All right, you'll eventually be forced to learn it one way or another. So with that, I want to switch gears one last time to talk about just algorithms in general. I want to teach you a pattern for making algorithms. A lot of the time you can break down your algorithm into two things: commands and then state. So think about state first. Like think about your program as like it's a bunch of different states that you could move around between. Like sometimes your program's in this state, sometimes your program is in this state, the line state, and then sometimes maybe your program's in this like checkerboard state. Think about your program. Sometimes it breaks down in this way. Like sometimes the program's working in this way, or in this way. And then a lot of the time, input moves you into different states. So like maybe you start your program here, and then some input takes you to this one, and then some extra input takes you here, and then finally you come back. Like that moves you between the states, some commands that the user kind of gives you, the input. So a lot of the time you can break down your program in this way, and I have a cool way to write programs if they do break down this way. It's not all of them will do this, but some of them will, and I have news for you. All right, this is one way of writing a program. So there's a bunch of different like competing architectures and patterns for designing programs. We call them design patterns, and everybody has their favorites, but here's a fun one that will work if your program breaks down in this way. It's got a bunch of states and commands that move you around between states. All right. It will answer this question in the affirmative because there is a cool cookie cutter way. It's just like you plug and chug, you fill in your problem in this way, and it will make a good program, a beautiful program, in my opinion, and then a program that's hard to get wrong as well. So that's good news for you. All right, if you don't buy the rest. So it's called a state machine. All right. So if you can break your program down into commands and states, then you can abstract it in terms of a state machine. All right. State machines abstract these processes that move you around between states. So here are some diagrams. So you're just going to draw a bunch of diagrams. Upper division computer science, guys, is a bunch of circles and arrows. Get ready for it. So here's the idea. Let's talk about this one first. So a state machine is made up of a bunch of circles, or oval things, I guess, rounded rectangles. And so those are your states. Those circle things are your states. And then transitions are the things with arrows, and usually there's words attached to them. These are arrows, and they kind of tell you exactly what you can do in your program. All right, so you model it on paper and then you implement it. So let's say that you make a program like this. Here's just a silly example of a state machine that models how a very boring human lives their life. All right, so let's say that this boring person has only 3 states that they ever go in. They're either in the work state, the home state, or the bed state. Let's say that they're born at home, so there's a concept of a starting state. So like they wake up and they're in the home state, let's say, or like they get powered on. If they're a robot, they live in the home state to begin with. That's their starting state, and then you can take some transitions to move you around. So maybe it's time to go to work and you want to move to the work state. Notice that the state machine tells you how you can do that. You can go there only by following the take train transition, okay? And that will move you into the work state. There's no other way to get there. That's kind of nice. You only have that one option. And then if you want to go home, then you have to take the transition again in the opposite direction to get back to your home state. And then you have dinner, and then it's time to go to sleep. So you want to go to the bed state, and so you use the sleep transition to do that. And then your alarm wakes you up, and you follow the wake state back to the home state, or the wake transition back to the home state. I hope that all these words make sense, right? So this doesn't really make sense for a program, but it makes sense for a person, right? But notice that by spelling out exactly what you can do, the different states you can be in, all the different ways you could follow those transitions and move between states, that also tells you exactly what you cannot do, which is very, very powerful, all right? Notice how, if it's time to, maybe, here are all the things that you could do. Like, maybe you go to work and then you have lunch at home. You can do this. Like, it's okay to do it like this. And then maybe it's the weekend. Oops. And then maybe it's the weekend, so you stay in bed and you stay at home twice. That's a possibility for sure. So all those things are allowable, but notice how it is impossible to go straight from work to bed. You're not allowed. The state machine is forcing you to go through the home state in order to get to the bed state. And that's super, super powerful. That's enumerating all the things you can do and also all the things implicitly that you cannot do. You can't go wake up out of bed and go straight to work. That's impossible. All right, that's very powerful, and I hope that makes sense to you. It's spelling out exactly what you can do, all the things that you're allowed to do, and implicitly then it's telling you also all the things that you cannot do. And so here's a better example of a state machine for a program. This is a state machine for an Uber app or a Lyft app, like a ride-sharing thing. So here's a state machine, and let's say that its start state is this. Like, you are the user, you've just requested a trip in Uber, and they're going to come pick you up. All right. So here's kind of what's going on under the hood in the Uber app. You request your state, your trip, that starts you in the trip requested state, and then you want to, you got to hit their credit card, so you go to the payment requested transition to get to the payment state, and then hopefully you follow the payment success to get a driver assigned to you. And that's the step. Those are the steps. Now a driver is assigned, you're in that state, and then they come pick you up. You wait, and you get out of their car. The trip is now complete. You follow that transition, and then the driver goes back to their unassigned state, and then there's some final charging of the credit card for real or something in the end state, something like that. There's other weird stuff, like if the customer canceled, that'll also get you out, get the driver unassigned. But this is kind of how a program for Uber would work. Does that make sense? And if you were to program this, I'll show you how. Do you see that you can have some very strong guarantees that you're never going to get in somebody's car, like the Uber app will never allow somebody to get into a car without first paying. That is super, super powerful and good to know if you're writing that app, right? You want to make money. So you must go through the payment state, to get to a driver assigned state. You cannot get in somebody's car unless your credit card checks out. That is very powerful. I hope that makes sense to you. And so if you were to program this in this way, to turn this into the Uber app and make this the real program, you will never get free rides. And that's what you want if you're Uber, right? That's very, very powerful and very, very useful. I hope you see that. Okay? So make these, model your program in this way, and then that'll tell you what you can and can't do. All right? So just in general, you want to group your program into states and then actions that you can perform on those states. So here's one last silly example before I go to real code. As a student, let's say that I'm going to give you, I'm going to model you as a state machine, just for fun. All right, I think of you in terms of my class as a 2-state machine. You have 2 different states in my class. You have the learn state and the practice state. Okay. You're just going to go between the two as I do stuff. but you start the class in the learn state because I haven't assigned anything yet, so that's the starting state. And yeah, just as I give you stuff to do, you'll go and you'll switch between those states. So as long as the lecture's not over, you can stay within the same state. You can follow a transition that keeps you there, that's fine. While the lecture's not over, you stay in the learn state. If I assign a lab, that's time for the practice state. And you keep working on that until lecture happens again. And then when lecture is going, you transition from practice to learn and pay attention, right? Stuff like that. So that's your state machine. And yeah, that's kind of how that works. There's a concept of an initial state. That's initial state. That's your learn state. That's where you start the class. There's also a concept of a final state. States that you should be in when your state machine is done, like when you turn off the thing. So the final state that we had, this is the initial state. Your final state in this class, you mark that with a double circle. So practice. Practice is going to be the final state for you, my students in this class, because the very last thing I give you in the class is going to be the final exam. There's nothing left to learn. Okay? Not until the next class, at least. So that is, that's how I can model you as a state machine, and I hope that makes sense. All right? So it's very, very like open-ended, but hopefully from this Uber example, you can see the power of it. All right? If you turn this into a program. So for my last thing, I want you to try this before I go to real code. I'll show you a cool example of state machine in actual code soon, but I want you to try this first. Here's a state machine for a traffic light. I got you started, so traffic lights can be in the green, the yellow, or the red state. I'd like you to fill it in with transitions, all right? And also like make some start states, like figure out what's the start state for this state machine. What should it all be, right? There's a bunch of different correct answers, but I want you to think about this. Like, what's the starting state for a traffic light? It's powered on. What state should it be in? And then what are the transitions that move you between all these different states of these lights? Think about it. All right, I hope you tried it and thought about it hard. Here's what I might think about this. Like, hopefully when you plug in your traffic light, it starts everybody on red, because otherwise very bad things would happen, right? I think that's a good starting state for the traffic light. And then now we need some transitions, right? So maybe the traffic light should be able to go from red to green, right? That's a normal thing that traffic lights do. That's a transition. And what are we going to call this transition? All right? What causes this to happen? So maybe like there's like a sensor usually, right? There's a sensor that detects a car. Detects a car waiting. That's a transition that we could have. And then we should also make sure that no other lights are green. That would be a problem. So like that's could be our transition that gets us from red to green for this particular light. Does that make sense? Is that kind of what you came up with? And then, all right, now it's green. It should be able to go from green to yellow, right? That's a thing. You can't go straight to red unless something weird happens, but it should be allowed to go to yellow, right? For sure. How long does it take to go from green to yellow? Maybe there's like a timer that's taken down, like maybe 30 seconds later. Or maybe the cars are gone, or something like that. That can be your transition to yellow, and then it depends on the speed limit of the road, but let's say that like 3 seconds later, it stays yellow, right? 3 seconds later, it transitions from yellow to red. Something like that, all right? Are there any others that you could think about? There are blinking yellow lights, so it could stay in yellow if something weird happens. Same with, like, it could be blinking red when there's like a power failure. That's on the backup power. So there's ways to stay in a state. And that's the thing, like when the power goes out, I guess you could go straight from green to red in that situation, and then it would start blinking red. But this is good enough. It just forces you to think of all the ways that you could move around between the states, and that's very powerful. You can turn this into a program. This is legitimately what's going on inside of a traffic light. They have modeled it, or you can think about it for sure, in terms of a state machine. All right. So that's the idea. In particular, there should be no state going from red. Let's see, like red to yellow doesn't make sense, right, for a traffic light. And like you can enforce that fact by programming this into your code. Okay. For your traffic light. So here's my last example that's actually a useful one for like I'm finally going to code rather than modeling humans and traffic lights. All right, I'm going to write code to do something using a state machine, and it's cool. All right, so let's make a state machine that counts words in a string. So somebody gives us a string, and we count all the words in it. All right, that's the goal. And so like somebody gave us, like the user gives us a line, like we use getLine or something. We have a line variable. and I'd like to count every word in this line. That's my goal. And this is a non-trivial problem. If you think about this, right, the user could have given you weird things. You might be saying like, oh yeah, it's very easy to count words. Just like count the spaces and add 1. That is not going to work in general. All right, this is a non-trivial problem, because maybe the user like gave you this string, like, all right, hello space world, a bunch of spaces, right? They could throw you off by doing that. Blah, space 42, something like that. Maybe that's your string. And you want to count the words in this. Do you see that is a non-trivial problem now? All right, I'm going to show you how easy this is if you turn it into a state machine. All right, and by the way, this is an example of a program that I learned when I was in your position, when I was taking CSCI 40 at Fresno State. So I'm passing this knowledge on to you, and so you have to promise now that if you ever become a computer science professor, that you give this example to your introductory programming students. Okay, we just have to pass it on from now on. So I thought it was such a cool example, and so let's go through it. So what we're going to do is we're going to have our state machine read characters one by one out of the string. We're going to go from left to right. We're going to like read the H, read the A, read E, read the L, the O, all those characters in order. And we're going to keep track of the white space that we see, all right? Because that is important, even though sometimes the user can trick you with multiple white spaces. And so it could have been a tab here as well, like tab or new line even. So we're going to check for white space with the isSpace function from the library, from the CC type library, right? So we're going to use that for sure for checking spaces. And we're going to run our characters one by one, and those are the characters themselves are what are going to transition our state machine, all right? And so what we're going to notice is that white space, yes, it separates words. That's a key thing, all right? And our state machine is going to take advantage of that, all right? Even if there's multiple spaces, it'll still work, what I'm about to show you. And then every non-space character, if you think about it, like this H, is either part of a new word, like this H is part of a brand new word, or like the E, it's part of an existing word, okay? So it's either part of an existing word or start of a new one. Like this W is start of the new word, but the O is existing word, all right? Another character of it. So here's the secret. So here's the state machine that's going to count words. You got 2 states. You are either outside of a word state, or you are inside a word. You got the inside a word state. All right? And you're going to run each of your characters one by one through the state machine. And the starting state is because you haven't read any characters yet, like you're outside the string, you're for sure outside of a word at the start. All right, so that's where your state machine starts. And then let's talk about transitions. So if you are outside of a word, when are you inside of a word? Like, that's when you see the H, right? You're outside the word, you see that first H, that's part of a real word, right? That's when you see a non-space character. I hope that makes sense. You see a non-space character, that should bring you inside of a word now. Now you're inside of a word state. And the second you see an E, like you're still inside of a word, aren't you? You're still inside of that same word. So as long as you keep seeing non-space characters, non-space, you're still inside of that word, okay? But after, like the comma, then you see the space, you're inside of a word, you see the space now, you are no longer inside of hello, are you? So if you were inside of a word but you see a space, that word is over. Now you're back outside of a word. And this is any kind of white space, tabs included, new lines included. That's why we're going to use this function. And then, yeah, you do the same game all over again. And eventually you'll get to here, like you're inside of a word, space brings you outside, and then more spaces, right? You're still not in a word yet. So you still see more spaces outside of a word, you're still outside of a word. Space. That's the trick there. Okay, I think that's all that I wanted to say, so notice that it's going to work, and it's going to go back and forth, like you see the H, that brings you from outside to inside. You see the E, that keeps you inside. The L, the O, they keep you inside, right? Comma space. Finally, that space brings you to outside of a word. Like, you can run this through your state machine. And if you think about it enough, like, we want to keep, like, a count variable. And we want to, like, start it at 0. We want to increment every time we see a brand new word. Okay? I claim that just one of these transitions is the one that notices a new word. Do you see which one it is? It's going to be this one. All right. If you were outside of a word, but you just saw a non-space character, that is the beginning of a brand new word. Does that make sense? So if you just always add one to your count right here, whenever you follow that transition, it will work and it will correctly count the number of words in your string. It's really cool. So here, let's try it. So we start outside of a word. That's our starting state. That's where we are right now. And we start running this machine with each of the characters in our string. So we start with the H character. And so that's a non-space character. So we follow this transition. We're now inside of a word, and we add one to our count. All right. Then you see the E, still non-space. You're still inside the word. The L, the O, the comma, still inside of that word. Hello. Okay. This was this transition a bunch of times. But then you see the space. You were inside of a word, but you're now not part of hello anymore. The space is not part of hello. You follow this transition to get outside of a word. Okay? Now we're in the outside of a word state, and we immediately see a W. That is a word character, right? So we were outside, we just saw a non-space character, so we're back inside of a brand new word. See that? So it's going to notice the world is beginning. So now we got 2 in our count. It's supposed to be a 2. Boop. And so now we're inside of a word, and as you can imagine, for the O, the R, the L, the D, the exclamation point, it's just this transition. We're still inside of that same word, okay? But then when we see spaces, we're going to transition to go to outside again. We're now outside of any word, and as long as we keep seeing spaces, we're still outside of a word. We're going to follow that transition. Does that make sense? But then when we see the B, we were outside, but now we're inside because we saw a non-space character. And following that transition, we should always add one to our count. And then the L, the A, the H keep you inside. The space brings you back outside. That's where we are now. And then you see the 4 character. That's a non-space. So you go follow the transition from outside to inside, add 1 to your count. You see the 2, and you're still inside because it was a non-space. And that's where your state machine ends. It was ending on this state, and like that's it, right? Because count is what you care about now. And do you see how it correctly counted the number of words in this string? That's very, very cool. That's a non-trivial problem. You can't just count spaces. This is kind of the cleanest way that you can do this. So like this is what's going on under the hood when like Microsoft Word is open or Google Docs is open. It's counting your words in this kind of way. All right? It's really, really neat. So let me show you now how to turn this state machine into code. All right, let's code it up. We'll turn it into a library as well with separate files after we do it first. All right, let's do it first though. And I think I don't need this slide. Perfect. So here, I'm gonna eventually turn it into a library though. So here, let's go out and make a new folder called, I guess I'll call it count words. Boop, and I'll cd inside of that. That's where we're gonna put everything. All right. So I'll compile. So now I'm inside this blank folder, count words, and yeah, let's kind of start it up. So let's say let's make a file with I'll just call it countwords.cpp first, and then we'll turn it into a cool multi-file library, the main function in a different file. But let's start it like this. Let's just pretend we have what we have, and so we'll be like, all right, let's get a line from the user with getLine, and we'll ask them ever so nicely, enter a line of text. We're going to count the words in that text. Now you know that line was a reference parameter too, because it's changing. So there's that, and then let's say that I want to call my function count words on the line, and it should give back the number of words in that line, so I'll print that out. And that is how I want to use my function. And so it's going to be int count words, right? Count words, and it's going to take a string that I want to count all the words in. Let's see, how do I want to do this? I'll just call it S, string S, okay? And this could be a very long line, so let's get it by reference. And I just want to be able to go through, right? I'm just going to look at the characters. I'm not actually going to touch and mess with the characters in the line. So this should have been a constant reference. Does that make sense? That's very important. So yeah, it's a count words function, and now our job is to run this state machine on this string that we were given, all right, to count all the words and give back the count. Are you ready? So the way that you implement a state machine is you just like remember what state you're in. So just use a variable to figure out, like, am I in the outside of word state, or am I in the inside of word state? And I'll just use a string for that. I just need to keep track of what state I'm in right now. So I'll call it string state equals, and my starting state is outside of a word. I'll just call that outside in all quotes. All right, that's one way to do it. And then I want to initialize count to 0 for sure, right? Because I'm counting stuff up. And then I'm going to do my magic, and then count holds the answer. That's what I'm going to return. All right, so this, now I just need to run the state machine. And I hope you can see that, like, by using a variable that keeps track of what state you're in, it's just going to be like, you're going to reset that variable a bunch of times as you're going through this string. And just like an if statement tells you which transition to follow, kind of. So here, let's go through every character of this line now. So what I want to do, right, is run the state machine on every character in the string s. So for every, let's go use indices, for every index in the string, from 0 to size -1. Oops. So let's call the current character we're looking at, I'll call it, put it in a variable. My current character that I'm looking at right now, current char, is equal to s at my index that I'm looking at. So that's the current character I want to run through the state machine right now. All right, and it depends, like what we do, right? It depends on what state we're in right now. If we're in the outside of a word state and we see a space, we stay there. If we see a non-space, we move, transition, add one to our count. But if we were in the inside of a word state, we saw a non-space, we stay there. If we see a space, though, we transition to outside. Like there's no adding one to count either. Like, so it changes. It changes depending on the state. So either what we do right now depends on what state we're currently in. So we have to like branch based on that. So if my state is outside, if I'm in the outside of a word state right now, I'll run my character. So that's important. And then I'll run the state machine in that way. Otherwise, I only have two states, right? So if that's true, then my state must have been inside. That's what I'll use to mean the other one. And then I have different things to check for and different ways to move around, different transitions to take. All right, but let's say that my state was outside. If that's true, what do I do? So if I'm in the outside of a word state and I look at my character that I'm looking at right now, like I'm seeing the H or something, it was a non-space character. So if I see a non-space, I need to do something special, right, and transition. If I see a space character, I stay where I'm at. I stay in outside of a word. Okay? So it all depends on whether or not is space is true or not for my current character. That's what's going to transition me. So if the current character is a space, so if is space, current char gives back true, then I'm doing stuff. And remember that this is redundant. It's just like is space current char. That's how you can read it. That's how it should be. Cleaner that way. So if the current character is a space, what do I do? Well, nothing really. Just stay outside. You're still outside. Nothing has happened. So just for fun, I can have a blank body, or just for fun, I will just say state is outside. Keep it as it was. Otherwise, though, that means it was a non-space character, right? Otherwise, non-space. If we were outside and we get here, we just saw a non-space character, so we must follow this transition. What does that mean for us? We need to transition our state to inside of a word and then also add one to our count. That's how we must implement it. So our state becomes inside, and then count plus plus. Okay, that's what happens. And so that's how you run the machine if you're in the outside state on your current character. If you're in the inside state, we have other things to do, right? Either it's non-space or space again, and then it kind of depends. All right, so a lot of this is the same. All right, it is a little bit different though, because we don't count anymore. So notice that if you're in the inside of a state and you do see inside a word state and you see a space character, you are going to outside. So like this first part is correct. That's correct for the inside state. For the non-space part, though, it's wrong. So if you're inside of a word, you see a non-space character, you just stay there, no adding to count. You're inside the same word. So I've got to get rid of that. Does that make sense? That's going to be the implementation of the state machine. It's just a bunch of ifs, if-elses. Depending on what state you're in, run it, figure out what transition to go on for your current state. That's pretty much it. All right, and so I'm running that for every character in my state machine, or sorry, in my string. I'm running it through the state machine, transitioning, and I guess this is the magic. It's keeping track of every new word I see right there. That's very important, that line. And then once it's done, it's returning that count back. So let's try it. Let's see it run. Oops. Let's make sure it compiled. Count words. Yay, enter a line of text. What do we got? Let's do exactly this one. Hello, comma, space, world, exclamation point, 3 spaces, blah. And you can have as many spaces and even tabs as you want. Put 42 over here, put some extra spaces at the end even. It's always going to do it right. Isn't that beautiful? So 4 words. Beautiful. Lovely. It's doing it correct. And like it does it for anything that you give here. Hi mom, tab, 42, 3 words. Awesome. So I think that's the example. Isn't that fun? I think that's really cool. And so let's take this example. Let's make like a count words library. All right. So we'll use separate files and make it cool like that. So here, let's say that count words is a function that can be part of my count words library. It's the one thing in the library. Okay. So I'll make a header file for that. I'll say count words.h. And that's where I'm going to put the declaration, right, of my library. Like everything that exists in the library that the user gets to see between the header file guards goes here. That's this count words. All right, and that's that. And then let's see. I'll have to mess with this in a second. I'll come back to this. All right, and then count words.cpp should hold the implementation, right? Should hold the implementation, the main function, all that stuff goes somewhere else. So the implementation of the count words function goes in count words.cpp, and customarily you include your header file for fun. Okay. We'll need to do more in just a second, but we'll get there. And then the main function goes in a third file. Let's put it somewhere else. I'll call it main.cpp. And it better include our library if we want to use it, right? Include countwords.h. That's kind of the setup. And now there's some things that need to change. So here. In the header file, it doesn't actually know what strings are because we need to include that, right? This line uses something in the library for one, in a library, and some other library for one, so we have to include string to have access to the string type. And then also, string by itself is not enough. It's you'd have to like use namespace standard or something because it's really standard : string. And what I want to tell you right now is you cannot use namespace standard in this file. I'm going to put all caps. Do not use namespace standard in a header file. That is not allowed. All right, you should never do this because think about what happens when you include a header file. You're copying and pasting all this code. Anybody who didn't want to use namespace standard is now forced to use namespace standard because if you say this, that's getting copied and pasted into their file. We do not force things upon our users. All right, you cannot have that. So the only way to get this working is you must say standard : string here. There's no way around that. All right, it is bad practice to do using namespace standard in a header file because that's forcing something upon the user. We do not want that. All right, so you got to do it this way. But in the implementation file, you can use namespace standard all day long. That's just for you. So using namespace standard is fine. And we get strings for free because it's going to be copied and pasted out of here. That's beautiful. And then also we need CC type, right, for is space. So that'll go here. I can go there. And I think that's the implementation. So it's just the function. Customarily, you include the header file. This is what we need for the function's implementation. We're getting string for free out of this one. We can use namespace standard all we want. All right, and then there's the normal implementation. And then back in the main file, let's see. We need strings, we need the library, and I think that was it. Yeah. Should be good. And it should still work. All right, so let's talk about how we just broke it down. So here, we got that one there, and there's the header file. So here, all these 3 files now are working together. We got the main file, main.cpp, with the main function that includes and uses the library. We have the header file for the library that declares all the things that exist in it that the user gets to see. Then we have the implementation file for the library that implements all the things that we promised to implement in the header file. Okay, so now to compile it, you give, remember, all of the implementation files, so just the CPP files, and then you can call it whatever you want. I'll call it main, and it'll still work. Hi mom, 2 things. Okay, I hope that makes sense. So that's pretty cool. That's splitting it up, getting some practice with that. And then the final thing is, let's remember how to make tests with assert true. So let's turn our example into a test rather than asking the user to type stuff. So instead of this, we'll turn it into a test. I'll call it like, usually a unit test is its own little function. I'll call it test count words. That'll be my little testing function. I'll put it up here. And it will use assert true. All right, so I need to include that right now. So let me quickly find it. Let's get it over here maybe. Lecture, this is 13, so 12 has something somewhere. Was it counter that had the test? I think it was. So counter slash, what do we got inside of counter? Main.cpp in the counter, right? There it is. Beautiful. So there's my assert true. I'm gonna steal it, put it right here. And then let's get rid of all these other ones. Cool, so in the main file now, instead of asking the user for something, let's make a test using assert true for our something. So let's make like a string, right? String s equals that one example, right? Let's do hello, comma, space, world, exclamation point, space, space, space. We can add even more things, blah, and then like even any white space, new line, tab, it's up to you. Space, 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 42. So that can be my string, okay? And then what do I want to assert true about my library? I want to assert that if I try to count the words, right, of that string s, then the number of words is exactly 4. Yes? That's what should happen. So count words in a 4-word sentence. And that can be one test. Compile, run, and cool, it passes. And remember, when you're testing, you should always try to test all the corner cases, all the things that might go wrong. So what are some weird edge cases for this count words thing? Like I was saying, like if there's a loop, make one that goes through the loop just once, like maybe make a 1 size string go through the loop no times at all, so make a 0 size string, because that would skip over the whole loop, make sure it all works. All right, so those are some good candidates for tests, and so I'd like you to try those yourself. Here's just one example. Like, let's do an empty string. Or maybe even more insidiously, let's make a string with a few spaces. All right, still the number of words should be 0. All right, so these are like our edge corner cases that we're thinking of right now. We're counting the words in a 0-word sentence, so the answer should be 0. See that? That's what we're checking against. Does that work right now? It should. So cool. And that's the kind of thing that's the game that you play when you're trying to test your stuff. Think of all the ways that could go wrong. Think about the edge cases, the corner cases, all that fun stuff. All right. So this is still a 3-file library kind of thing. And now we're testing stuff too. All right. So I'm going to give you all this code. Remember, go back, study it, and ask me lots of questions about it if it doesn't make sense. But I think that's officially everything I wanted to talk about. We are very good at functions now, I hope. All right. Yell at me if you have any questions, but that is the last slide for functions. We have more to talk about later. It's a different topic, but you should pat yourself on the back because this is a very, very, very powerful ability to make our own functions, and now you have it. All right? So, yeah, congratulate yourself, and I will see you later.